Hey everyone. Hi, so today I'm going to be deriving something called the continuity equation. And what the continuity equation is it's one of the most important equations, well, one of the most, two important equations in fluid dynamics and electromagnetism. And it really shows the conservation of mass. Okay, that's what it shows. And so how does it go? So say you take an arbitrary volume element. Here's my volume element here. That's not a good drawing, so I'll start again. Here's my volume element here. Okay. And just to show it's a volume. And you place this volume element in a field. The field we're going to place it in, well, we're going to be using, okay, 1 second. So I'm going to take, just as a little side note, we're going to take the normal to be pointing outwards, okay? So you place it in a fluid, actually. We're going to place it in a fluid. And this volume element has a volume V0, so an arbitrary volume V0. So we place it in a fluid, and density of this volume, rho, is dependent on the position and the time. So it's not necessarily constant density. It can vary over time, and it varies over wherever you are in this volume element. So the density could be different over here to here. Okay, the molecules could be dependent on how the fluid's hitting it. And so the fluid's going to be flowing through all different angles. Okay, the fluid's flowing through this element here. Okay, and one of the most important things is that this element has a closed surface here, S. It's got a closed surface. And so what we're going to say is we want to find out what is the mass of this volume element here. What is the mass? So, as we know, the mass is just generally we generally have the formula density rho is equal to mass divided by volume, where density has the units kilograms and per meter cubed, kg or kilograms per meter cubed. Okay, so that's what density is, but we want to find out what is the mass of this volume element here. And so we can say the mass is equal to the integral over the whole volume element of the fluid density function, rho, with respect to the volume. Okay, so we're integrating over the whole volume. And what's important is that this volume is, we're going to take a snapshot in time. And this volume, we're going to go over the whole volume, and it's going to be fixed. Okay, we're going to do a volume integral over the whole volume, right? And so we can say, well, what is the change in the mass? What is the change in mass at a certain time? Well, the change in mass is dm by dt. But from above here, we have that m is equal to this. So this is equal to d by dt of the integral of, over the whole volume, of rho dv. Okay? Now, we have a special case. So this density is dependent on, so this rho here is dependent on a position and a time. And so this position, r, might have several coordinates. So if we take it in the Cartesian coordinate system, it'll have an x, it'll have a y, and it'll have a z coordinate. So if we want to, but the problem is, each of these will depend on time. At a certain time, they'll have time in it. And so if we want to find out the change in mass in time, it's not as simple as differentiating it with respect to time, because we'll have multiple variables in here. So what we have to do is we have to take a special case of something called the Leibniz integral rule. Okay, I'll just put it as a small side note up here. You can have a look. It's the Leibniz. Oops, sorry. It's Leibniz integral rule. We're in a special case here, okay? And so this becomes, you can have a look at this, at the Leibniz integral rule. This becomes the integral over v naught of partial d rho by dt, by partial d rho by partial time with respect to dv. So that's our first representation of the change in mass. Now we want to move on to a different representation, an equal representation. So let's just keep this as a side note for now and move down a bit. Okay, so I'm just going to take the surface of our volume element here. So here's our volume element here, and here's just the surface now. We're just looking at a 2D view, and it's a closed surface. And so we've still got the fluid flowing through the surface, and it's still got the same density. We're just taking it in a 2D view here, okay? So here's the surface. We want to define a quantity, J. We want to define this quantity to be rho times Q. So Q is the velocity, okay? Q is the velocity, and rho is the density. So what is J? What is J? Well, let's just take a look at the units of J first. So J has units, rho, which is kilograms per meter cubed, and velocity has units, meters per second. So doing a little bit of multiplication, we have kg m minus 2s minus 1. So what is this? This is really, it's kilograms per meter squared per meter square second. So what J is saying is, it's saying how many kilograms have I got that is flowing out of this per area every second. So every second that goes by, if I take an area, how many kilograms is going through this every second over my area? So here's my area A. How many kilograms of kind of water have I got for my area every second? So I can count this, right? That's what J is. And J has a name, and the name of J is the mass flux density. And we'll see more of this when we come to electromagnetism by flux. J is the mass flux density. And essentially, again, what it is it's the amount of kilograms of fluid that is flowing through our area every second. So that's what J is. And J has an outward flow. So, again, if we want to find out what the mass is, we can say, well, that's the same as saying, it's not a volume anymore, we're going to take a surface. Okay? Take our surface, I'm going to denote this as partial dv naught, because I'm taking a closed surface of a volume element. And we're going to integrate the closed surface of J with respect to S. So this is a surface integral. Okay, this is a surface integral. So this is the same as the surface integral over our surface S, which I'm going to denote as partial dv of the rho times Q ds dot ds. So we're going to take a surface integral. And so what the surface integral Now we can use a special trick. What we're going to use is we're going to use Gauss's law. Gauss's law. Okay, called Gauss's theorem. And what Gauss's theorem says is it says we can rewrite this as, instead of a surface integral, we can go up a dimension, and we can write this as a volume integral. And we can say this is the volume integral of, now Gauss's theorem says we have to put the divergence of J into here. Okay, that's what Gauss's theorem tells us. And this is over dv now. So we've gone from a surface integral over to a volume integral. And now we have a new representation of the mass outflow. Right? And the problem is, since it's a mass outflow, we're going to have by convention, we'll just put a minus sign to denote an outflow. Right? So we have these. Now, this is our mass outflow here, right? And this is the amount of change of mass per time. So the change of mass per time is the outflow of the mass integrated over the volume, right? So we're gonna equate these. So if we equate these, we have, just changed here, we have this formula from earlier, dv is equal to our new, thanks to Gauss, our new formula here. So we equate these, and so since it's an arbitrary volume v0, they're both over the same domain, we can just take this over to this side, and this is now the integral v of, I'm just going to use angular brackets just to denote. Now, by properties of integration, we can, linearity, we can put that into the integrand, and we have this. Okay? And of course that's equal to 0 because we just took it over to the other side. But because the integral, because the integral is 0, that implies that the integrand must be 0 up to a constant. Okay? So the integrand is 0. So then we have that partial d rho by dt plus the divergence of j, which is rho times q, is equal to 0. Okay? But that implies, that doesn't imply, but now we can use a property of the divergence to say this is the same equivalent as this is equivalent to partial d rho by dt plus, now we have to use the property of divergence, so this is rho times the divergence of q plus q times the divergence, times the gradient of rho, and that's equal to 0. But this here and this here is just the material derivative acting on rho. Okay, this is just the material derivative acting on rho. Okay, so let's rewrite that as the material derivative. Oops, sorry, it should be the other way around. There we go. So you should have a look at the material derivative. That's the same as the material derivative plus we have this extra term here. And hence this is now the continuity equation. And we have three different variants. The first variant is steady flow. The second variant is constant density. And the third variant is incompressible fluid. that leads to the Laplacian when it's irrotational.